In a factory outside Nanjing, a machine is spitting out a bar that looks like it belongs in a bicycle frame. It is thin. It is dark gray. It weighs about a quarter of what a steel bar of the same size weighs. And when engineers put it in a testing rig and pulled on it until something had to give, the bar held on to more than 2,000 megapascals before it finally let go. Ordinary construction steel gives up at around 400. That is not a small improvement. That is a number that makes people check the machine, then check the sample, then check the machine again. When those results started circulating in European engineering circles, the reaction was not excitement. It was suspicion. A German structural engineer, speaking to a trade publication, said the figures were physically plausible, but commercially implausible, which is a very polite, very German way of saying, sure, you can make that in a lab, but nobody can make that by the 1,000 tons at a price anyone will pay. Except China is making it by the 1,000 tons, and the price keeps falling. This is the story of how a material that Germany and Japan invented, refined, and dominated for 40 years quietly slipped out of their hands. It involves a fiber thinner than a human hair, a furnace hot enough to melt granite, a trade blacklist that backfired spectacularly, and a bridge in Jiangsu province that was built without a single kilogram of steel reinforcement. But before any of that, you need to understand why steel has been so hard to replace in the first place. Steel is one of those inventions so successful that we stopped noticing it. It holds up the building you are sitting in. It runs through the concrete under the road outside. It is the skeleton of every bridge, every ship, every wind turbine tower, every parking garage. Humanity produces roughly 1.9 billion tons of the stuff every year. If you piled a single year of global steel production into one cube, it would be taller than most skyscrapers. And the reason we use so much of it is not that steel is exotic. It is that steel is boring in exactly the right ways. It is strong. It bends before it breaks, which gives people time to get out of a building. It welds. It bolts. Every engineer on the planet learned it in school. Every building code on the planet is written around it. Every insurance company on the planet knows how to price it. That last part matters more than people realize. A material does not win because it is better on a spec sheet. It wins because 1,000 institutions have already agreed on how to use it, test it, certify it, and pay for it. But steel has a problem, and the problem is not strength. The problem is rust. Water gets into concrete. It carries chlorides from road salt, from sea air, from the ground itself. Those chlorides reach the steel bars buried inside, and they start eating. Rusting steel expands. It swells to several times its original volume, and it does that inside a hard shell of concrete that has nowhere to go. So the concrete cracks. The cracks let in more water. More water means more rust. More rust means more cracking. Engineers have a grim little phrase for this. They call it the concrete cancer cycle, and it is the single largest maintenance bill in the developed world. The United States spends tens of billions of dollars a year fighting it. Germany has thousands of bridges that were built in the post-war boom and are now, all at once, reaching the end of their patience. In 2024, a bridge in Dresden simply fell into the Elbe River in the middle of the night. Corrosion of the internal tendons was a central line of investigation. Nobody was on it. That was luck, not planning. And the bill is not just financial. Every repair means lane closures, detours, and years of disruption. A single major bridge rehabilitation in a European city can tie up traffic for 2 or 3 summers running. Multiply that across a national network built in the same 20-year window, and you get an entire country trying to fix its arteries at the same moment, with the same limited pool of contractors, using the same material that failed the first time. So the entire industrial world has known for decades that if you could build reinforced concrete without putting rustable metal inside it, you would solve a problem worth hundreds of billions. The answer was obvious. The answer was carbon fiber. And here is where the story turns. Because the answer has been obvious since roughly 1970. Carbon fiber is not new. A Japanese researcher named Akio Shindo worked out a key process in the early 60s. British researchers at Farnborough pushed it further. Then Japanese companies, Toray above all, spent decades industrializing it. Germany built the machinery. The two countries together effectively owned the field. The material itself is almost absurd. You take a plastic precursor, usually polyacrylonitrile, and you spin it into a fiber. Then you stretch that fiber and heat it, first to a few hundred degrees to stabilize it, then to well over 1,000 degrees in an oxygen-free furnace. Everything that is not carbon burns away or gases off. What survives is a thread of nearly pure carbon, aligned along its length, thinner than a human hair. Thousands of those threads get bundled into a tow. The tows get woven, or laid straight and soaked in resin, and the result is a material that is stronger than steel for its weight by an enormous margin, and completely uninterested in rust. You can leave it in salt water. Nothing happens. So why is every bridge in the world not made of it? Money. That is the entire answer. Money. For 50 years, carbon fiber cost somewhere between $20 and $50 per kilogram, and the good stuff cost far more than that. Steel rebar cost well under $1. That is not a gap you close with clever engineering. That is a gap that keeps a material locked inside. Formula One cars, fighter jets, satellites, and very expensive tennis rackets. The industry accepted this. Toray and its Japanese rivals, along with a handful of American and German players, ran a comfortable, high-margin, low-volume business. They controlled the precursor chemistry, which is genuinely the hard part. They controlled the furnace designs, they controlled the supply, and they controlled the price. And then, because the material is also useful for missiles, centrifuges, and stealth aircraft, governments controlled who was allowed to buy it. Which brings us to the export controls, and to what may be the most consequential strategic miscalculation in modern industrial policy. Starting in the 90s and tightening through the 2000s, high-performance carbon fiber was placed under strict export restrictions. Japan and the United States and their partners restricted the sale of the highest grades to China. They restricted the sale of the production equipment. They restricted the sale of the precursor technology. The logic was straightforward. This is dual-use military material. Do not hand a rival the ability to build better missiles. And on the narrow question of slowing down a specific weapons program, the controls probably worked for a while. On every other question, they backfired completely. Because when you tell a country with a manufacturing base the size of China's that it will never be allowed to buy something, you have not stopped that country from getting it. You have simply given it a national mission, an unlimited domestic market, and a guarantee that whoever solves the problem at home will face no foreign competition at all. You have removed the risk from the investment. That is exactly what happened. The Chinese effort did not begin with a triumph. It began with about 20 years of failure that almost nobody outside the industry noticed. The first attempts, running through the 80s and 90s, produced fiber that was inconsistent, weak, and full of defects. This is where the outside world got its long-running assumption that China could not do this. And the assumption was, for a time, correct. The reason is that carbon fiber is not one technology. It is a chain of technologies, and every link has to be nearly perfect. Start with the precursor. The polyacrylonitrile has to be polymerized to an exact molecular weight with an exact distribution. Then it is spun through a spinneret, a plate with thousands of holes so small they are measured in microns, into a chemical bath. If a single hole clogs slightly, you get a defect that runs the entire length of that filament. If the bath temperature drifts by a degree, the internal structure of the fiber changes. If there is a speck of dust in the room, you get a void. A void becomes a crack. A crack becomes a broken toe. A broken toe shuts down the line. Then comes oxidation, where the fiber is held at high temperature for hours while it chemically rearranges itself. Too fast, and it burns. Too slow, and the line is uneconomical. Then carbonization, in furnaces at well over 1,000 degrees with no oxygen, where roughly half the mass of the fiber leaves as gas. Those gases are corrosive. They eat the furnace from the inside. Managing them is a genuine engineering discipline of its own. Then surface treatment and sizing, because a bare carbon fiber does not bond well to resin, and a fiber that does not bond to resin is a very expensive piece of string. Every one of those steps has to run continuously, at high speed, for weeks at a time, with tolerances that are basically invisible. And crucially, none of it can be reverse engineered from a finished sample. You can buy a spool of Japanese carbon fiber, cut it up, put it under an electron microscope, and learn almost nothing about how it was made. That is why the export controls looked so smart. The knowledge was in the process, and the process was locked in factories nobody was letting anyone tour. So China did the slow thing. It built the process from scratch. The turning point came in the 2000s, and it is associated most closely with a company in Jilin province and a researcher named Zhang Guoliang, along with parallel work at institutions across the country. The state poured money in through national research programs. Universities were assigned to the problem. Provincial governments funded plants that lost money for years. By Western financial logic, most of these operations should have been shut down. They were burning capital on a product they could not sell competitively. But the goal was never the next quarterly result. The goal was the capability. And when your goal is the capability, a decade of losses is not a failure. It is tuition. By the mid-2010s, the fiber coming out of Chinese lines had reached what the industry calls T700 grade. Respectable, usable for wind turbine blades and pressure vessels and sporting goods, not the top tier, but real. By the early 2020s, Chinese producers were shipping T800 and demonstrating T1000 class material. That is aerospace territory. That is the territory the export controls existed to protect. And then the second thing happened. And the second thing is what actually broke the old order: volume. Because China did not just learn to make good carbon fiber, it learned to make an enormous amount of it. Between 2018 and 2024, national production capacity multiplied several times over. Jilin, Jiangsu, Shandong, Zhejiang. New lines, then new lines beside those lines. Not boutique facilities producing a few hundred tons a year, plants designed for tens of thousands. And volume does something to cost that no laboratory breakthrough can do. When you run a line at full capacity around the clock, your fixed costs spread thin. When you run 100 lines, you generate more process data in a year than the incumbents generated in a decade. Every jam, every break, every batch that came out slightly off, all of it feeds back into the next line design. The price of standard-grade carbon fiber in China fell hard. In some grades, it dropped by more than half in the space of a few years. Product that used to be quoted in the tens of dollars per kilogram started being quoted in the low teens, and for some industrial grades, lower still. That collapse rippled outward immediately. Western and Japanese producers who had planned expansions found themselves staring at a market where the price had moved beneath their cost floor. Some expansions were quietly shelved. Some plants ran below capacity. The comfortable, high-margin, low-volume business stopped being any of those things. But the price drop is only interesting because of what it unlocked. And what it unlocked is the part that has structural engineers genuinely rattled. Once carbon fiber gets cheap enough, you stop using it only in fighter jets. You start using it in concrete. This is where China moved fastest, and where the gap with Europe is most visible on the ground. Instead of steel rebar, you use bars made of carbon fiber bound in resin. Instead of steel pre-stressing tendons, you use carbon tendons. Instead of steel mesh in a repair layer, you use a carbon grid a few millimeters thick. The consequences are not incremental. They are strange. A carbon rebar weighs roughly a fifth of the steel bar it replaces. A crew that needed a crane and 4 men to place a bundle of steel can carry the equivalent by hand. Transport costs collapse. Site logistics simplify. Nothing needs a protective coating because there is nothing to protect. More importantly, the concrete cover changes. With steel, you must bury the bar deep inside the concrete, because that thick outer layer is the only thing keeping water away from the metal. That cover is dead weight. It does almost nothing structurally. It exists purely as armor for the steel. Take away the rust risk, and you can take away most of the armor, which means thinner slabs, thinner walls, thinner bridge decks, which means less concrete overall, which means less cement, which means a meaningful cut in the carbon emissions of the structure, which matters because cement production alone is responsible for something in the range of 7 or 8% of global emissions. So you get a lighter structure that lasts longer and emits less, all from swapping out one component. And, because carbon fiber does not corrode, the design life of the structure stops being governed by chemistry. A conventional reinforced concrete bridge in a coastal or de-icing environment is often designed for 50 to 100 years and frequently needs major intervention long before that. Non-corroding reinforcement moves that conversation into a completely different range. There are real objections to all of this, and the German engineers raising them are not being stubborn for the sake of it. Their objections are serious, and they deserve a proper hearing. The first one is brittleness, and it is the big one. Steel is ductile. Load it past its limit and it yields. It stretches. It sags. It gives you cracks you can see and deflections you can measure. A steel-reinforced structure warns you before it fails, and that warning is not a nice bonus. It is baked into the safety philosophy of every building code on Earth. Carbon fiber does not do that. It is elastic right up to the end, and then it snaps. Full strength, full strength, full strength, nothing. There is no sag. There is no warning. In the language of the profession, the failure is sudden and catastrophic. A German engineer looking at a Chinese carbon-reinforced bridge is not doubting the tensile numbers. He is asking a different question entirely. What happens on the bad day? What happens when a truck twice the legal weight crosses it in a storm after 30 years of fatigue? With steel, you probably get a very expensive repair. With brittle reinforcement, you might get something worse. The Chinese and international answer to this is hybrid design. Combine carbon reinforcement with a smaller amount of steel, or with fiber types that fail more gradually. Design the system so that something ductile gives before the carbon does. Add embedded sensors, strain gauges, fiber optic monitoring so the structure reports its own condition continuously rather than relying on a visible sag. That last idea is genuinely elegant. If your material will not warn you, instrument it so it warns you electronically. But it also means the safety of the structure now depends on a monitoring system continuing to function and be maintained for decades. Some engineers find that a reasonable trade. Others find it deeply uncomfortable. The second objection is fire. Steel loses strength in a fire, but it does so predictably, and codes account for it. Carbon fiber composites are held together by a polymer resin, and polymers do not enjoy fire. The fiber itself handles heat well. The resin holding it in place does not. Above a few hundred degrees, the bond can degrade, and a fiber that is not bonded to the concrete is not doing its job. This is not unsolvable. There are high-temperature resins, geopolymer matrices, fire protection layers, and design approaches that assume degraded performance under fire loading. But it is another chapter that has to be written into codes that currently do not have that chapter. The third objection is the least glamorous and probably the most powerful: standards. You cannot build a public bridge out of a material that the national code does not recognize, no matter how good it is. In Germany, in the EU, in North America, that means committee work, working groups, draft standards, public comment, ballot, revision, publication. It means insurers pricing risk on materials with limited long-term field data. It means municipal engineers who are personally liable signing off on something new. That process is not corruption or laziness. It is how you avoid killing people with it as an untested idea. But it moves at the speed of institutions, and institutions are not fast. There is also the question of who trains the workforce. A steel fixer learns his trade over years. Tying carbon rebar is a different craft, with different tolerances, different cutting equipment, and different failure modes on site. A bar that is nicked by a careless grinder can lose a meaningful share of its strength, and unlike steel, it will not bend to tell you it is unhappy. Building that skill base across an entire construction industry is a slow, unglamorous problem that no laboratory result solves. China has been quietly running that training program for a decade through its pilot projects. Europe has largely not started. China's process is not faster because Chinese engineers are less careful. It is faster because the state can decide that a technology is a national priority, direct that pilot projects be built, fund the testing, and compress the feedback loop between research and deployment. When the same actor sets the standard, funds the research, and owns the client, the loop closes in years instead of decades. Which brings us to the actual proof, because none of this would matter if it only existed on paper. Across China, there is now a growing catalog of built structures using non-corroding reinforcement. Bridge decks in coastal Jiangsu and Zhejiang where salt air used to shorten service life. Marine structures, docks, seawalls, and tunnel segments where chlorides are relentless. Repair and strengthening work where existing bridges are wrapped in carbon sheet to extend their lives without rebuilding them, which is now a mature global technique and one China performs at massive scale. There are cable-stayed structures using carbon tendons, which is a natural fit because the enemy of a long span is the weight of the span itself. A steel cable long enough eventually spends most of its strength holding up its own mass. Replace it with a cable, a fifth, the weight, and the maximum theoretical span jumps enormously. Longer bridges become physically possible, not just financially difficult. And then there is the sector where this has already been settled quietly for years. Wind turbines. Modern turbine blades are enormous. Some designs exceed 100 meters from root to tip, longer than a football field, rotating in the air, subject to fatigue cycles for 20 years. Steel is not remotely an option. These blades are composite structures, and carbon fiber spar caps are what allow them to get that long without collapsing under their own weight. China builds a very large share of the world's wind turbines, which means that the demand for industrial-grade carbon fiber inside China is not a hypothetical future market. It is a real, enormous, daily consumption that keeps the plants running at capacity, which keeps the cost falling, which makes the material affordable for the next application. There is a similar story in pressure vessels, hydrogen storage tanks, compressed natural gas cylinders, breathing apparatus for firefighters. All of them are wound with carbon fiber because the alternative is a steel bottle so heavy nobody can carry it. As hydrogen infrastructure expands, that demand grows with it, and it grows in exactly the same factories. The same is true of rail. Chinese train manufacturers have been testing composite car body structures and bogie components, because on a train that accelerates and brakes thousands of times a day, every kilogram removed is energy saved forever. And in shipping, composite superstructures cut weight high above the waterline, which improves stability in ways naval architects have wanted for decades but could rarely afford. That is the loop. Volume drives cost down, low cost opens new applications drive more volume. Once it starts turning, it is extremely hard to stop from the outside. And this is the part that European producers understand better than anyone, because they have watched it happen before. Solar panels. Germany invented much of the modern photovoltaic industry, subsidized it heavily, built world-leading companies, and then watched Chinese manufacturers scale up, drive costs down by an order of magnitude, and take the market almost entirely. The technology was not stolen. It was simply out-manufactured. Lithium batteries. Largely a Japanese and American invention, refined in labs in Oxford and Texas and Tokyo, now overwhelmingly produced in China, with the chemistry, the machinery, the refining, and the supply chain all concentrated there. High-speed rail. Imported German and Japanese technology in the 2000s, adapted, extended, and now operating on a network longer than every other country's combined, with China exporting the systems. In each case, the pattern is the same. The West invents. The West prices for margin and builds slowly. China builds enormous capacity, absorbs years of losses, drives the cost curve down, and then owns the volume. And once you own the volume, you own the learning. And once you own the learning, the technological lead follows the manufacturing lead, not the other way around. Carbon fiber is running that same play right now in public, and everybody in the industry can see it. So, is steel actually obsolete? No, not remotely. And anyone claiming otherwise is selling something. The world will produce nearly 2 billion tons of steel this year, and probably more next year. Carbon fiber global production is measured in the low hundreds of thousands of tons. The ratio is not close. It is not going to be close in your lifetime. Steel is still cheaper for the vast majority of uses. It is still tougher, more forgiving, and vastly better understood. But obsolete was never the right question. The right question is whether steel's monopoly on structural reinforcement has ended. And that answer is clearly yes. In a specific and expanding set of situations. Anywhere salt water is involved. Anywhere de-icing salt is used. Anywhere weight is the binding constraint. Anywhere the maintenance cost over 60 years dominates the construction cost on day one. Anywhere the electrical or magnetic transparency of the reinforcement matters, which turns out to include hospitals with MRI machines and certain rail and research facilities. That set of situations used to be a rounding error, because the material cost 20 times too much. It is not a rounding error anymore. And it is getting larger every time the price drops another few dollars per kilogram. There is one more thread here that most coverage misses, and it is the strategic one. Export controls are supposed to deny capability. What they actually do, when applied to a country with the manufacturing depth to respond, is guarantee that the country builds the capability domestically, without foreign competition, with state backing, and with a permanent motivation never to depend on the controller again. You do not get a dependent customer, you get a permanent competitor, and you lose the customer at the same time. The carbon fiber restrictions were designed to keep advanced material out of Chinese missiles. Today, China has domestic, high-grade fiber, domestic precursor chemistry, domestic furnace manufacturing, and enough surplus capacity to export into the markets that once supplied it. The restrictions did not prevent the capability. They just made sure it was built somewhere else, at scale, by someone with no reason to share. That is not a Chinese victory that was won purely by Chinese effort. It is partly a gift, handed over by a policy that assumed the hard part would stay hard forever. There is a real argument on the other side, and it deserves to be said plainly. Cheap is not the same as safe. Fast standardization is not the same as good standardization. A material that has been in the ground for 8 years has not proven it will be fine in 80. Some of the German caution is exactly the caution that keeps bridges standing, and it would be reckless to dismiss it as protectionism or wounded pride. The Dresden Bridge fell because of a failure mode that took decades to develop and gave almost no warning at the surface. Brittle reinforcement is a category of risk that nobody has yet observed across a full structural lifetime, and honest engineers on both sides will admit that. But caution has a cost too. Every year a country waits, its existing infrastructure keeps rusting on schedule. Germany has thousands of bridges that need work now, not after the Standards Committee reports. And the longer the wait, the further ahead the manufacturing base gets, and the harder it becomes to catch up even after the codes are ready. That is the real bind. It is not a technical argument at all. It is an argument about how much risk a society is willing to take in exchange for speed, and different societies answer that differently, and both answers have consequences. What is not in dispute is where the material is being made. The thing that started as an obscure Japanese laboratory process, that spent 40 years locked behind price and export restrictions, that Europe and Japan treated as a permanent high-margin specialty is now rolling off Chinese production lines by the tens of thousands of tons a year at prices that were considered impossible a decade ago. The bar in that Nanjing testing rig is not magic. It is not a scientific breakthrough that nobody else understood. Every equation behind it has been in the public literature for half a century. It is a manufacturing achievement, which is somehow both less impressive and far more threatening, because you can protect a secret with a classification stamp. You cannot protect a cost curve. Steel is not going anywhere. But for the first time in 150 years, it has to compete for jobs it used to get automatically. And the company competing for them is not in Essen, or Nagoya, or Pittsburgh. If you found this useful, hit subscribe. We break down the industrial and technology shifts that get one line in the news. And here is the question I want your answer to. When countries adopt a new structural material fast, accepting that some risk is unknown, or wait for decades of data while its existing bridges keep aging? Tell me in the comments.